Hi, good day. Today we will continue with the chapter 3, System of Linear Equations, with the second method of LU factorization method, which is Cholesky method. So let's continue. So Cholesky method, okay. When you want to solve the system of linear equation using Cholesky methods, the first thing that we need to know, we need to make sure that a matrix A must be symmetric, positive, definite. So based on the previous that we learned about, okay, how we are going to solve that is a similar start from the ax equal to b. For the Cholesky method, we have to make the A become L and L transpose. Okay, L transpose, okay, L is the lower triangular matrix. So let's say we have like this A11, A12. Let's say we have 3 times 3 matrix, A13. If lower, that means lower here, okay, we will have a value. So at this point above the diagonal line, there will be a 0. Okay, this is a lower triangular matrix. And when we do the transpose, that means the row here, we make it become column. The first row, so let's say this is a L, okay, so L transpose, okay, will be, so this will become A11 and then 0 0, okay, and then the second row, this one, okay, become in the second column, so become A21, A22, 0. And then the third column will become a third row become the third column of transpose matrix. A31, A32, A33. Okay. So the U, this is the previous that we learned before using Thomas method. This is a U. So U now is changed to transpose lower triangular matrix. Okay, going back to just now, I mentioned that when we want to solve the system of linear equation using Cholesky method, we have to make sure that the matrix A is symmetric, positive, definite. Okay, so how we can find whether this matrix is a symmetric, positive, definite using 3 methods. So using we want to check, we want to recognize whether this matrix is a symmetric, positive, definite by definitions, and then or rule or even theorem. We can use theorem to check it. Okay, so I will continue for the first method, which we can use by definition to check whether that matrix is symmetric, positive, definite or not using the definition. So by definition, so if you have the book, you can turn in your page. Page 53. You can refer to your page, page 53, when it said that Matrix A is a symmetric positive definite if X transpose time with matrix A times X is larger than 0 for any X is not equal to 0. Okay, so we try the example. What is mean here? So maybe we just check whether the matrix A is symmetric positive definite matrix or not using this example. Okay, let's do example 3.13. Okay, page 53. Said that show that matrix A so that matrix A is symmetric positive definite by using definition. So we will use this one. We will check. Okay, so for this one, the X mean normally we use like this, right? X1, X2, X3. This is the matrix of X because here we have three unknowns. Okay, three equation with three unknowns. Then X transpose will become X1, X2, X3. Okay, this is a X transpose. So solution, we do the solution here. Okay, X transpose time with matrix A time with X. So become X transpose is X1, X2, X3. Matrix A is 3, 1, 0, 1, 3, negative 1, 0, negative 1, 3 time with X, X1, X2, X3. So because this is a 3 matrix multiplications, so I will do the multiplication step by step. So we will start with these two first, multiplication of these two matrix. Okay, so here this is a 3 times 3 matrix, and this one is 3 times 1 matrix. So when we multiply this matrix 3 times 3 multiply with matrix 3 times 1, so we'll get 3 times 1 matrix. Okay, so here become x1, x2, x3. Okay, and then here, so if let's say here row time with the column. So the first row will be 3x1 plus with x2, okay? Plus with 0, okay? And then the second row time with this column. So become x1 plus 3x2 minus x3. Okay, and then the last row time with the column become here, okay, 0 x1 plus with, okay, negative 1 time with x2 become negative x2 plus 3x3. Okay, so become like this. And later on, we will use multiplication. We will solve these two multiplication of the matrix, where this one is the 1 time 3 matrix, 1 row and 3 columns, and this one is 3 times 1, 3 row and 1 column. When we do the multiplication, it will become 1 times 1, so it become 1 line. So it will become x1 times with 3x1 plus x2, and then plus with x2 times with x1 plus with 3x2 minus x3 plus x3 times with negative x2 plus 3x3. And then 3x1 square plus this x1, x2 plus with x1, x2 plus kita kembangkan ya. 3x2 to minus x2, x3 minus x2, x3 plus 3x3 square. Okay. So because here we got x1, x2, and here we got 2. Okay, so I will write it again. 2x1, x2 plus 3x2 square minus 2x2, x3 plus 3x3 square. So because since this one, we can try to do the factorizations, okay? Where I will use this one, become x1 plus x2 square, and then over there is x2 minus x3 square, but then we still lack of, we need another 2x 1 square plus if x2 square plus if 2x3 square. So okay, I show you this one. When we do x1 x1 plus x2 square, that means so basically we'll get this one plus 2x1 x2 plus with x2 square. So if you look at here, this one, but we still need another 2 x1 square. So that's why here I put plus 2x1 square. So if let's say not here, go to this one. When I do this one, saya faktorkan factorization of this one become this one x2 square minus 2x2 x3 plus x3 square. So when you look at here, okay, this is done. Okay, this is done. Okay, this is done. Okay, same as this one. This one also okay, already done. But here, just now, this one we lack 2. We need another 2x1 square. And here we have 1x square, x2 square. And here we have another one, x2 square. So here already got 2. But here we total have 3. So that's why I add another one, x2 square. And then for the x3 square, when we do this factorization, we only have x3 square. But originally we have 3x3 square. So that's why I add another 2x3 square. Okay. So when we have this one, you see all of this is in a square, 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 square. So no matter whether the x is positive or negative, our value for sure will be positive. So that means it will be, for sure, it will be larger than 0. Let's see. Let's say, as example, we take x is -1. So for sure, when you put x -1 plus -1, that means negative 2. Okay, we square, for sure we get, let's say here like this. And here, -1 minus -2 square. Negative, this one becomes 0. And then okay, this one becomes 0. And then this one, -1 square become 1, right? So plus with this one become 1, plus with 2, 1. So for sure our value will be positive. it won't be negative. So it will be larger than 0 for sure. So but when this is negative, if let's say x is positive, for sure every when we do the multiplication, when we do the calculation, it for sure will be larger than 0. So it's mentioned if let's say this one x transpose time with matrix x time with x is larger than 0 for any x, for x not equal to 0, if larger than 0, that means this matrix A is symmetric, positive, definite by using definition. Okay. Okay, go to the second. Okay, this one, okay. So we go to the second one is by row. Rows. Okay. So using rules. So if let's say using rules, okay, you may refer to the page 53. Okay, it's same. Okay, the matrix A for a square matrix n times n will be is a symmetric positive definite. Then okay, at here we have a 4 rows. Okay, row 1, row 2, row 3, row 4. So we start with the row 1. The first rules, it said that A is non-singular matrix. Okay, what is non-singular? Okay, matrix A is a matrix A is non-singular if the matrix A, that means n times n, that this is a square matrix, such that okay, A times B equal to B times A equal to identity matrix. What is B? B is the inverse matrix of A. Or we can say that inverse matrix is determinants matrix A. Or we can write like this: determinant matrix A cannot be equal to 0. Ataupun in this like this, it cannot be 0. That means this matrix A is non-singular. That means that the determinants of matrix A cannot be 0. So how we are going to find these determinants? Okay. So how to find determinants A? Okay, so basically we have 3 methods to find the determinants of matrix A. Okay, so let's go to the first. The first method. Okay, first method to find maybe we just direct take the matrix A just now, using example 3.13, the same example just now. Let's say we have matrix A like this: 3, 1, 0, 1, 3, negative 1, 0, negative 1, 3. Okay. Okay. Just to make sure that I'm recording. Okay. So remember your last, I think maybe in your form 5, maybe or form 6, or maybe I think in the secondary school that you learned before, when we want to do for example, this one is metric 3 times 3. We want to do the determinants, we have to do like this. Okay. So I will start with the using this value. this 3, I will put in the front here. Okay. So, and then I will cross the same rows and then same column. Okay. Exclude those value and then I will choose this value and then put in here. So become 3, -1, -1, 3. Okay. And then the second one, I have to put the sign of negative and then continue with the second value of here. Okay. This is 1 and do the same. And here as well, I will exclude the same row and then same column. So become this value, which I will put in this matrix. So become 1, -1, 0, 3. And then the last one, plus, okay? It will be plus negative, positive, because here it's positive, negative, positive. Third one will be this value, put in here, time with the cross the same row, same column. So become 1, 3, 0, -1. So for sure, this one, because time with 0, so all of this will become 0. So we do the next, we have to solve these determinants by here, this 3 times 3 minus with the -1 times -1. We'll do the cross like this, 3. That means we'll do 3 times 3 minus -1 times with -1. Okay, minus, okay, so here same, this one times this one minus this one. So become 1 times 3 minus -1 times with the 0. So, and this is a 0 lah. Okay, so and then continue. Okay, 3, this means this is a 9 minus 1 minus 1 times 3, 3. So 9 minus 1, 8. 8 times 3, 24. 24 minus 3 become 21. So 21, that means this is not 0. Okay? So this matrix A is non-singular. Okay? Non-singular. Okay, this is the first method to find the determinants matrix. Okay, so the second method to find determinants is, okay, I will write back the matrix 3 times 3 just now. 3, 1, 0, 1, 3, -1, 0, -1, 3. And I will write back the 2 column here to the right. Okay, 3, 1, 0, and then 1, 3, -1. Okay, I just write back. Okay. Oops. Oh, cannot be delayed. I write back 3, 1, 0. Okay. So now I will use this one. I will, okay, use this one. Okay. So this diagonal line, this diagonal line, and this diagonal line, I will do the multiplications amongst this value, and then same to here, this one as well. Wait, just now this is -1. Okay. So this one, okay, 3 times 3, 9. 9 times 3, 27. Okay, 1 times -1 become -1. -1 times 0 become 0. And this one, 0 time, okay, 1 and time negative 1 becomes 0. And here, 0, 3 times negative 1, negative 3, negative 3 times negative 1, 3. And this one, 1 times 1, 1, 1 times 3, 3. Okay, so, and then I will use determinants A. Let's say this is a matrix. Will become, I will use this value 27 plus 0 plus 0 minus with 0 minus plus 3 plus 3. So become 27 minus 6. So become 21. So it's the same. Okay. So I get the same value just now. Okay, this is the second method. Okay. And then the third method, we will have the third method. To find determinant is using calculator. Okay. So let's say, let's do using calculator. Let's see this one. Okay. I will key in. Okay. So for this calculator, we have to choose matrix. So matrix is number 4 here. So now I go back again. Okay. Sorry. Matrix. We go to this number 4. So let's say we define our matrix as matrix A. So we choose number 1. Okay. So the number of row is 3 rows and 3 column, like 3 rows, and then how about column? Also 3. So we'll get matrix 3 times 3. So key in all the value here. This is the 3 equal to 1 equal to 0 equal to 1 equal to 3 equal to negative 1 equal to 0 equal to negative 1 equal to 3 equal to. So we already get this matrix. So I just press AC. So I'll go to the option here. So I want to find the determinant. So I choose none. You have to press down. Okay. Choose determinant. That is number 2. So it come DET. So DET what? D3 matrix A. So we have to go to the option again and find matrix A. This is 3. So you press 3. So you press equal to. So you get 21. So this is the determinants of matrix A. So for those who are using this older version of calculator, so this one I will show you. You go to the modes option here and find matrix. That is option 6. So you press 6. And then if you ask you matrix, okay, so you want to define the matrix as matrix A or matrix B or matrix C. So I just define it as matrix A. So I choose 1. So how about the row and column M times N? So that is M is 3 times 3, okay? Matrix 3 times 3. So I choose number 1. So it's come out this matrix 3 times 3. I key in all the value. 3 equal to 1 equal to 0 equal to 1 equal to 3 equal to negative 1 equal to 0 equal to negative 1 equal to 3. Okay. And then press AC. Don't press on, press AC and then go to shift 4. You look here. Can you see here there is a matrix? Okay, so you have to press shift and then 4. So you find this one, number 7, determinant, DET. Choose 7. Okay, so we want to find determinants of matrix A. So that means we have to find matrix A. So go to shift again, click number 4. So matrix A is number 3. So choose 3. And then equal to. So you get 21. Okay. Okay, so this is only the first rules. Okay, first rules of we want to find whether the matrix is symmetric, positive, definite or not using rows. First rows. Okay, we have another 3 rows to go. So the second rules. The second rule is said that AII larger than 0 for all or for any I is equal to 1, 2, and until n. Okay? So that means if let's say we have a matrix just now, this matrix, right? This matrix. Let's say we have this matrix. So I write it again. Zoom in again. 3, 1, 0, 1, 3, negative 1, 0, negative 1, 3. Okay. So if I write in it, normally we write in here, right? 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay. So matrix II, that means that it's the same. If let's say we have matrix 3 times 3. So we will have matrix 1, 1, A11, A22, A33. That means at this diagonal line here. That means AII for this one will means that A11, A22, A33 have to be larger than 0. So look at here. This one larger than 0. Yes, this one larger than 0. And this one larger than 0. Okay. So this matrix A11, A22, A33 is equal to 3. That means larger than 0. So this one is okay for the second row. So we go to the third rows. So the third row is said that maximum A Kj for k larger than 1, smaller than n, for j larger than 1, smaller than n as well, have to be less of equal to a maximum value of AII. Okay. So basically, J, okay, we look at here. J is actually Ij, right? I is basically is a column. J is the row. Sorry, I is the row, J is the column of the matrix. J. So let's say we start with the I equal to 1. Let's say start with the I equal to 1. That means our AII is A11, right? So we have A KJ. That means KJ will be A12 and also A13 for the same row. Okay. So it said that the maximum value of either A11 or A13 have to be smaller or equal to A11. So if we look at here, A12 or A13 have to be smaller or equal to A11. So look at here. Our A12, this one, right? This one. Sorry, I use another color. So A12, that means this one. A13 is this one. So either 1 or 0 have to be smaller than A11 is 3. So this one okay because this A11 is bigger. Let's say we took I equal to 2. That means AII is A22. And then AKJ will be A21 or A23. So we check whether A21 or A23 in the modulus is smaller or equal to A22. So A21, A21, A23. So this one and this one. So means 1 or negative 1 smaller than 3. Yes, this is smaller. And then when I equal to 3, This means AII is A33. AKJ will be A31 or A32. Sorry, A32. So either we want to check whether A31 is modulus or A32 smaller or equal to A33. So 31 is this one, 32 this one, 0 and -1. So this one is 0, -1. So yes, yes, can, because this one is larger. Okay, so when we check all this one, okay, so when all of this is okay, that means this is matrix A is symmetric positive definite using the row 4 to fulfill the third row. Okay, this is the third row. And one more row we have to fulfill in order to make sure this matrix A is the symmetric positive definite, the fourth row. The fourth row is set here. Aij square have to be smaller than Aii times Ajj. Okay, for all I and j is equal to 1, 2, and then until n. So because here we have matrix 3 times 3, so the n is until 3 only. Okay, so back just now, we check similar to just now. When we have, let's say, using a blue color, I equal to 1. Okay, so we check Aii is become 1, 1. Aij become, sorry, AJJ become A22 and A33. So Aij will be A12 and A13. So I will check whether for the first one A12 square smaller than A11 times A22. So we check A12. A12 is this value 1. So 1 square smaller than 3 times 3. Yes. Okay. And then check the second one, A13 square smaller than A11, A33. So A13 is 0. So 0 smaller than 3 times 3, 9. Okay, yes, this is okay. So for I equal to 1. And then I equal to 2, that means AII is A22 and AJJ is A11 and A33. So Aij will be A21 and A23. Okay. So we check A21 square have to be smaller than A22 times A11. So A21 is this one, 1. 1 smaller than 3 times 3. Yes. Okay. And then we check another one, A23 square have to be smaller than A22 times A33. And A23 is -1. Square have to be smaller than 3 times 3, that is 9. So yes, okay. Okay. And then for I equal to 3. That means AII is A33, AJJ is A11, and A22. So AIJ will be A31 and A32. So we check similar to just now. A31 square have to be smaller than A33 times A11. So 31 is 0. Have to small. Then 9. Okay. And then A32 square have to be smaller than A33, A22. So A32 is -1. Square have to be smaller than 9. Okay. So this also okay. So when all of these row 1, row 2, row 3, and row 4 comply, that means When all of this okay, that means this is the matrix A is a symmetric, positive, definite, using the rules. Okay, so the third one is, okay, so this is done using the rules. Now we go to the theorem. We go to the theorem to check whether this matrix is symmetric, positive, definite or not. Okay, using theorem. Theorem. So you can refer to in your books in page 54. So it said that a symmetric matrix A is positive definite if and only if and only if each of its leading principal submatrices has a positive determinant. Okay. So using the same matrix just now, let's say here, that's now the matrix, the same matrix 3, 1, 0, 1, 3, negative 1, 0, negative 1, 3. Okay, this matrix A. So what is its leading principal submatrix? So for the submatrix, okay, we have, this is the first submatrix, the second submatrix, and then a third matrix, submatrix. Okay, so that means matrix 1, and then matrix 2 times 2, and then matrix 3 times 3. Since we have matrix 3, this is a matrix 3 times 3. Let's say this is matrix 4 times 4, that means we have another matrix 4 times 4 submatrix. Okay, so we'll start with the first one. We have to find the determinants of matrix this one. So determinant of this one equal to 3. Okay, they are same. So this is a positive value because it said you have to be a positive determinant. The second one is determinant of matrix 3, 1, 1, 3. Okay, so this one we'll have to find using just now, similar to just now, this one times this one minus this one times this one. So become 3 times 3 minus 1 times 1. So 9 minus 1. So equal to 8. So this is positive as well. And then the third one, determinants of matrix 3, 1, 0, 1, 0, 3, sorry, 1, 3, negative 1, 0, negative 1, 3. So this one also we already find just now, become 21. So this is the positive value. Okay. So this is by theorem. Sorry, give me 2 minutes. Wait, okay, sorry class, we continue, okay. Okay, so we continue just now. Okay, when all of these determinants of submatrix of this matrix A is positive determinant, so this matrix can be said that it is a symmetric positive determinant using theorem. Okay, so another very simple way to to determine whether that matrix is uh, symmetric positive definite or not is like this. Let's say this matrix, back to this matrix, is we just from this diagonal line, right? This diagonal line, we do the image, mirror image. So it should be in a mirror image where this value have to be saved with this value, and this value have to be saved with this value, and this value will be same with this value. If we do the diagonal line and we kalau kita lipat this should be in a mirror. So in the mirror image, so those value are in the mirror image. So this matrix considered as a positive symmetric, symmetric positive definite matrix. Okay. So we go to the example how to solve the system of linear equation using this Cholesky method. Okay, so I move to the right. Okay, so we just take the example in your books. Okay, example 3.16. So 3.16, the matrix A. Okay, this is in page 55. Basically, the same matrix same as what we did just now. So solve the system of linear equation below using Cholesky method. This matrix. X1, X2, X3, 1, 2, 4. Okay, so the first step. Step 1. We have to make the A become L times with L transpose. Okay, so before this, we have to, for the Thomas method, we have to change A to L times U, lower trigonal matrix times with upper trigonal matrix. But this one, we only change to lower trigonal matrix and we just transpose it. So that means we have matrix like this: 3, 1, 0, 1, 3, -1, 0, -1, 3. So it will become matrix. Okay, this is will be 0. The diagonal line will have a value. Okay, 0, 0, 0. So this is a B, C, D, E, F. Okay, and we just transpose the balik kan, row become column. So A here, row become column. So A 0, 0, B, C 0, D, E, F. Okay. And then we compare element by element. Like the previous, we do the comparisons. Like I do in the table like this. In the matrix form, right? 3 times 3. So this is a 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3 matrix. So this one matrix, this one 3 is equal to first row times first column. That means A square plus 0 plus 0. So A become square root of 3. Okay. And then the first row, second column. This one equal to first row A times the second column. AB plus 0 plus 0. So B equal to 1 over square root of 3. Okay. And then D is the first row, third column. 0 equal to first row, third column. So A times with D. So because D is 0, that means D equal to 0. Okay. So this one, second row, first column. That means second row, first column. Second row, let's change to other color. Second row, first column. So 1 equal to AB. Okay, so you need we already solved, so no need to solve already. And then this one 3 equal to second row times second column. B square, this one, the second column. This is a B. Okay. So B square plus C square. So B already know, so we come C square. C square is minus 1 over 3. So 3 times 3, 9. 9 minus 1, 8. Okay, so 8 over 3 square root. And then this one, the second row with a third row, a third column, negative 1 equal to BD plus CE. Negative 1 equal to B. D is 0. This is a CE. So C, just now we already get, right? So E equal to 1 divide by this one, the balik kan, 3 over 8. Okay, and then 3, 1, 0 equal to AD. So this one no need to solve already because here got already. So D is equal to 0. And then negative 1 equal to BD plus CE. CE. So this same with this one. So we don't need to find already. So go to this one, the third one. 3 equal to D square plus E square plus F square. So D is 0. E is 3 over 8. Okay, because it's already squared, so become positive, plus F square. So F equal to 3 minus 3 over 8. So 3 over 8, 3 times 8, 24. 24 minus 3, 21. 21 over 8, square root. So when we get all the value here, so we can put our L is, A is this one, 0, 0, B, C, D is 0, E is, and then F. Okay, our L transpose will be okay. So now step 2, L times 1 y equal to B. So we solve y. So L is, our L is here, 0, 0, 1 over square root of 3, 8 over 3 square root, 0, negative 3 over 8 square root, 21 over 8 square root, y1, y2, y3 equal to the value just now 124. B is 124. 124. So here we use the forward substitution. Where start with this one, y1 equal to 1, y1 equals to 1 over equal to 0.5774. So you can use calculator to find this equation. So we just use the equation A. This one, oops, equal to, so number one, how many unknowns? 3 unknowns. So put up the value 3 and then 0, 0. Value of this one is 1 and then 1 over square root of 3 and then this one is 8 over 3 and then 0 and then 2 and then 0 negative square root of 3 over 8 and then square root of 21 over 8 and then 4. So we get 0.557 and then y value is 0.5774, 1.02, 1.0206 and then 2.8546. Okay, and then continue with the step 3, ux equal to y, where we will solve the x using backward substitution. So u is x1, x2, x3 equal to 0.5774, 1.0206, 2.8546. Okay, so using calculator, same A, polynomial 1, unknown 3. So key in the value 1 over 3 and then 0.5774. This is 0.5774 and then 8 over 3 negative square root of 3 over 8. Then 1.0206 and then 0, 0 square root of 21 over 8 and then 2.8546. Okay, and then you'll get x is equal to negative 0.0952 and then 1.2857, 1.7619. So this is the solution. So I think I end the class today for the Cholesky methods until now. So we meet you again, see you again next time.